You know, our world is constantly being built and rebuilt, all thanks to these powerful, invisible processes. We call them chemical reactions, and they are, quite literally, the architects of our reality, from the device you're watching this on to the very air you're breathing. So, have you ever stopped to wonder about something like this? Why is it that when you slice an apple, it turns brown? And, well, that's it. But a melted ice cube can easily just freeze right back into ice. The answer to that simple little question unlocks the huge difference between two fundamental types of changes happening all around us. And here's the secret. A physical change like ice melting just changes the form of something. It's still water, right? You can reverse it, no problem. But a chemical change? Whoa, that's a total transformation. It creates a brand new substance with a completely different identity. That's why you can't just unbrown an apple. Something new has been made. So, how can you be a detective and spot these transformations? Well, you've got to look for the clues. A sudden change in color. Think of that reddish brown rust on an old bike. A change in temperature that comes out of nowhere. Or maybe you see fizzing and bubbling, like when you drop an antacid tablet in water. These are all telltale signs that a chemical reaction is underway. Okay, so now that we know how to spot these changes, how do we actually write them down? Well, chemists have this universal language for it. Think of it like a recipe book for reality. Let's dive in and see how it works. Now, don't let the words chemical equation scare you. Seriously, they're not some complex, scary formula. Just think of them as recipes. They show you the exact ingredients you need and the final dish you're gonna get. It's basically chemistry's version of a cookbook. And every one of these recipes has two basic parts. On the left side, you've got your ingredients. We call those reactants. And on the right side, you've got the final dish. We call those products. It's just a simple before and after snapshot of the change. Now, this is where it gets really interesting. Chemistry has one single, unbreakable rule that governs every recipe: the law of conservation of mass. All it means is that you can't create stuff out of thin air, and you can't make it just disappear. Whatever you start with, you have to end with. And that is why we have to balance our chemical recipes. It's basically an atomic inventory check. You count out the atoms of your ingredients on the left, you count the atoms in your final dish on the right, and then you use these little multipliers to make sure the numbers match up perfectly. In chemistry, there are no leftovers and no missing ingredients. It all has to add up. All right, let's start meeting the different types of reactions. It's kind of cool. We can group them into families based on what they do. So first up, let's meet the master builders and the demolition experts of the chemical world. Combination reactions are the builders. They're the ones that take simple things, two or more separate substances, and construct something totally new and more complex. It's all about putting things together. And the formula couldn't be simpler. A plus B comes together to make AB. A really cool example is when you burn a magnesium ribbon. The magnesium combines with oxygen from the air in this brilliant flash of white light. And what's left behind is a totally new substance, this white powder called magnesium oxide. And then you've got the breakers, the decomposition reactions. And yeah, you guessed it, they do the exact opposite. They take one big complex compound and just smash it apart, breaking it down into its simpler little pieces. But how do you actually break a chemical bond? It needs a little push, usually in the form of energy. You can bake it apart with heat, you can zap it apart with electricity, or you can even use the power of light to split it. Each one is a different tool for deconstruction. Next up, we have a family of reactions that's all about trading places. I like to think of it as a chemical dance party where everyone starts swapping partners. So, in what's called a displacement reaction, you have a more reactive element that basically just muscles its way in, kicking a less reactive element out of its spot. It's like the more energetic dancer cutting in on the dance floor. Chemists actually have a ranked list to predict who's going to win the dance off. Let's watch this happen. Okay, imagine we take a plain old iron nail and we dip it into this really bright blue liquid, which is copper sulfate solution. At first, nothing much seems to be going on. But then, the magic starts. The blue solution slowly fades and turns green, and the iron nail gets this new brownish coat on it. So what happened? Well, the iron is more reactive, so it kicked the copper out of the solution and took its place. That's why the solution turned green. And the copper that got kicked out, it forms that new coat on the nail. Now, what happens if everybody at the party decides to switch partners at the same time? Well, that's a double displacement reaction. This is where two compounds meet up and they just trade ions, creating two completely new compounds, a total partner swap. And one of the coolest things you can see from this swap is when you mix two perfectly clear liquids, and like magic, a solid just appears and settles at the bottom. That solid is called a precipitate, and it's a dead giveaway that a double displacement reaction just went down. So here's the thing. These reactions aren't just happening in some far-off lab. They are happening everywhere, all the time. They are, quite literally, what makes our world go round. See, every reaction involves energy. Exothermic reactions, like a burning candle, release heat and make everything around them feel hot. But endothermic reactions do the opposite. They absorb heat, making their surroundings feel cold, just like one of those instant ice packs. Photosynthesis, the process that fuels pretty much all life on Earth, a classic endothermic reaction. And now, let's bring it all the way back to the beginning. That browning apple, that rusting piece of iron, both of them are caused by a super common type of reaction called oxidation. It's what happens when something combines with oxygen, and it is one of the most important chemical changes shaping the world we see every day. The truth is, you are a walking, talking symphony of chemical reactions. Every breath you take, every meal you eat, every single thought you have is powered by these invisible architects. So the next time you see something as simple as an apple turning brown, take a second to appreciate the incredible chemistry at play and ask yourself, what other invisible changes are shaping your world right this very second?